Okay, let's delve into using calculus along with physics to tackle some real-world challenges. In this video, we are going to explore this topic from 3 different perspectives, employing single, double, and triple integrals individually to arrive at the same equation for calculating the water discharge over a triangular weir in a channel. So, tingnan po natin ang mga images ng mga weirs kung saan sila po ay naka-install in various settings. So, ano po ang mga weirs at ano po ang gamit nila? So, ang mga weirs po ay mga barriers. They are engineered barriers specifically designed to modify or alter the natural flow patterns of water. Typically, they are constructed across rivers, streams, or other water courses or channels or dams, and they serve various purposes. At isa po dito ay ang pag-manage ng water levels, ang pag-control ng flow ng tubig, at ang pag-measure ng movement nito. Okay, now let's dive into the derivation. First, let's describe the geometry of the setup and define the variables we need to derive the equation. So this is the front view of the weir installed in a dam. This thing in blue is the water and its level is only up to here. Let's assume the height of the water surface from the triangle vertex is h, its width is w, and the vertex angle is theta. The weir is an isosceles triangle with the side at the left and at the right being equal in length. Therefore, if we divide the triangle like this, we end up getting 2 congruent triangles, and this angle here is theta over 2. Now, how do we compute the discharge? Discharge is calculated as the product of velocity and area. However, the velocity varies across the entire triangular region, so we cannot directly apply this formula. What we need to do is divide the entire triangular region into an infinite number of horizontal strips. Then, let's focus on this particular horizontal strip. Let this strip be at a distance y below the water surface, so its thickness must be dy and is virtually 0. Typically, the water in a dam has no current, which implies that only gravity is the net force that causes the water to discharge over the weir opening. So the discharge velocity at this level is given by v equals the square root of 2gy, and this is according to Torricelli's theorem, which can be derived from the law of conservation of energy. The reason behind chopping or partitioning the triangular region into an infinite number of horizontal strips is to render its strip negligibly thin. This guarantees uniform discharge velocity across the top and bottom of its strip, enabling the application of equation 1, which relates discharge to velocity and area. This method exemplifies the ingenuity and power of calculus, distinguishing it from algebra. Okay, now we can utilize equation 1 to calculate the discharge at this extremely thin horizontal strip. First, let's rewrite equation 1 in its fundamental form, which is dq equals v dA. And let's label this as equation 3. Now, dq is the differential discharge, which is the discharge at this extremely thin horizontal strip, while dA is its differential area, which is equal to its width, x, multiplied by its height, dy. And we will label this as equation 4. Now, using equation 2 and equation 4, we can rewrite equation 3 as follows. dq equals the square root of 2gy x dy. And let us call this as equation 5. Now, we need to express x in terms of y. So, how can we achieve it? Well, let's look at this triangle at the right, this triangle here. We can say that tangent theta over 2 is equal to w over 2 over h. Now, the opposite side to this angle, theta over 2, is w over 2. And the adjacent side to this angle is h. So, this is the equation for the tangent over 2. And let's call this as equation 6. Now, in the same manner, we can also write tangent theta over 2 by looking at this smaller triangle here. And so, tangent theta over 2 can also be written as x over 2 over h minus y. Now, in this smaller triangle, the side opposite to this angle, theta over 2, is x over 2. And its adjacent side is h minus y. And so we have these equations, and let's call this as equation 7. Okay, now let's equate equation 6 and equation 7. So we obtain the following. W over 2 over h is equal to x over 2 over h minus y. Now, we can solve x in this equation, and we are going to obtain the following expression. W over h multiplied by the quantity h minus y. Okay, let's call this as equation 8. Okay, and we also need to calculate or to solve for the value of w in equation 6 here in this equation, because we also need it later for the derivation of our final formula. So, solving for w in equation 6, we obtain the following. W is equal to 2h tangent theta over 2. And let's label this as equation 9. Now, let's rewrite equation 5 using equation 8. So, dq equals the square root of 2gy times x. Our x is w over h minus y, and then dy. And let's label this as equation 10. Okay, let's delete these stuffs here. Now, let's integrate both sides of equation 10. And the limits of integration is from y equals to 0 to y equals to h. Now the integral of the q is simply q. Now this term w over h is a constant term, so we can just write it at the front of the integral. This expression, the square root of 2gy, can also be split up into two. The square root of 2g times the square root of y. The square root of 2g is a constant term, so we can also write it at the front of the integral. And then the square root of y can be written as y to the power 1/2, and then multiplied by this expression, it's minus y, and then dy. The limits of integration is from y equals to 0 up to y equals h. So we can label this as equation 11. So what is the implication of equation 11? What does this integral imply? This integral implies that it chops up the entire triangular region into an infinite number of horizontal strips, calculates the discharge at each strip, and then adds up all the discharges of each strip, starting from the surface of the water at the top up to the vertex at the bottom to obtain the total discharge. So this is the theoretical discharge formula for a triangular weir, which we have just derived by applying the concept of a single integral. To determine the actual discharge, we simply multiply the theoretical discharge by the discharge coefficient CD. So the actual discharge would be 8/15 CD square root of 2G tangent theta over 2 h to the power of 5 halves. So this is the formula for the actual discharge. So this concludes part 1. In the next video, our task for part 2 is to examine the problem from a different perspective and derive the same equation using the concept of a double integral.